Hello, everyone. So thank you for attending the IRENET online seminar. So I'm Sota Kimura from High Energy Accelerator Research Organization, KK, Japan. So today we invited Dr. Tomoshi Takeda as a speaker. Before starting the uh, talk, I will briefly introducing to him. So he went to the Department of Physics at the Tokyo University of Science from his undergraduate studies through his doctoral programs. Additionally, he was affiliated with the Tamagawa High Energy Astrophysics Laboratory at RIKEN. He was involved in a study on developing the X-ray detectors for X-ray observation satellite called NinjaSat. After the satellite was successfully launched, he started to observational research on X-ray bursts. With this study, he got a doctorate in 2024, and he now belongs to the Department of Physical Science at Hiroshima University, Japan, as a postdoctoral fellow. So today we asked him to give us a talk about his development of the uh, X-ray observation satellite called NinjaSat and also a recent observation result. So Takeda-san, please start.
Thank you very much, Kimura-san, for the kind introduction. I'm happy to have the opportunity to present our recent work. Today, I would like to talk about X-ray burst observation, in particular about recent progress using a very small satellite called CubeSat. On the lower right, you can see a CRISM, an X-ray astronomical satellite launched by Japanese Space Agency JAXA 2 years ago. Traditionally, X-ray observatory have been relatively larger satellite, about 10 meters in size, like this one. In contrast, the satellite we developed, NinjaSat, is very small compared with CRISM. So what I'd like to show today is that even a small satellite can now perform astronomical observation. In particular, I'll show you our observation result of X-ray bursters obtained with NinjaSat. So here is the outline of my talk today. First, I'll briefly explain the background and the motivation of X-ray burst studies. Next, I'll describe the development of NinjaSat and its main instrument, the gas X-ray detector, GMC. Finally, I present the observational results. So let me start with the introduction of X-ray burst. As shown in this picture, X-ray burst occurs in an accreting neutron star system. Gas from the companion star flows towards the neutron stars, forming an accretion disk, and finally accretes onto the neutron star surface. In such a system, X-ray bursts are often observed. X-ray burst is a subnuclear explosion on the neutron star surface, and it is powered by sequence of many nuclear reactions, such as triple alpha reactions and RP process. So this figure shows the typical burst light curves. The emission is well described by black body radiation with a temperature of about 2 kiloelectron-volts in the X-ray band. The burst duration is about a tenth of seconds, releasing a total energy of about 10 to 39 ergs. So far, X-ray bursts have been observed from around 120 X-ray sources. So by comparing the observed property of X-ray burst with the recent theoretical models, we can use them as a probe to study neutron stars and their companion stars. So from observation, we can determine the quantity such as total energy, peak luminosity, and recurrence time. These observable allow us to infer the neutron star information, such as the neutron star mass and radius, equation of the state, the composition of the accretion gas, and the mass accretion rates. So although X-ray bursts occur on the neutron star surface, they can provide valuable information about the about not only neutron star but also the companion stars. So among more than 120 non-X-ray bursters, clocked X-ray bursters are ideal for comparing observation with theoretical models. So this is a special subclass of X-ray bursters, and only 7 such sources have been confirmed so far. So upper figure shows the right curve of a typical example, GS1826. As you can see, the recurrence time of the burst is remarkably stable. So some of you may be familiar with this Japanese shishiodoshi. This is a bamboo water fountain and that makes a regular knocking sound. So clocked X-ray bursters behave in a very similar way. So as shown in this movie, gas from the companion star gradually accumulate onto the neutron star surface, and once a certain amount is accumulated, an X-ray burst is triggered. So because of this mechanism, the burst recurrence time changes in a regular manner with the mass accretion rate. So the left figure shows the relation between the burst recurrence time and the mass accretion rate. So previous observations have shown that the recurrence time roughly follows an inverse proportional relation with the accretion rate. This means that the amount of fuel required for one burst is almost constant, and there exists a kind of critical mass. Critical mass. So just like the mechanism of CCOC. So this is a recent result by Johnson et al. They compare the observed parameters such as recurrence time and burst profile with the typical clocked X-ray burster GS1826 over 3 different epochs. From this comparison, they estimate several key parameters such as neutron star mass, radius, and composition of the accretion gas. So, however, from an observational point of view, because the recurrence time of X-ray burst is typically a few hours, long-term monitoring is required or essential. They are essential for such studies. So, but however, such continuous observation have become difficult with modern larger satellites. So in this context, we focused on the small satellite, especially CubeSat. So here I would like to introduce CubeSat and its potential in X-ray astronomy. So CubeSat is a class of a small satellite consisting of several 10 centimeter cubic components. So very small satellite compared to the conventional larger satellite. So as shown in the upper right figure, the number of CubeSat missions has been increasing recently. In recent years, and in also X-ray astronomy, CubeSat is beginning to attract attentions. So, as you know, satellite is necessary for X-ray observation because X-ray from celestial sources are attenuated by the Earth's atmosphere, and we cannot observe them on the ground. So we needed to launch the satellite. So in this context, CubeSat offers cost and time-effective solution compared to the larger satellite. So in addition, flexibility in observation planning is also an important advantage of CubeSat. For larger satellite, the observation time is shared among many users all over the world, and it is limited for each X-ray sources. So on the other hand, CubeSat can conduct a more flexible program, such as prompt follow-up observations and long-term observations. So we believe CubeSat has great potential in also X-ray astronomy, including observation of X-ray bursts, and started the NinjaSat project. So now let me move on to an overview of NinjaSat. NinjaSat is the first Japanese 6-2 CubeSat for bright X-ray sources. So unlike the previous CubeSat mission, NinjaSat is a general-purpose X-ray observatory for time domain astronomy. Such dedicated and agile CubeSat is suitable for long-term observation of persistently bright X-ray sources, as well as X-ray transient discovered by All-Sky Survey. In addition, NinjaSat has the world's largest effective area among CubeSat missions. And thanks to this large effective area, we can observe the many X-ray sources, more than 90. This represents the unprecedented capability of NinjaSat in CubeSat missions. So this is an overview of NinjaSat. NinjaSat is a 6U size CubeSat X-ray observatory. As shown in the left figure, the satellite has a size of 10 by 20 by 30 cubic centimeters, roughly the size of backpack. So the satellite bus system, which handles the function such as attitude control, communication with the ground station, has been developed by Nanoavionics, which is Lithuanian satellite integrators. This collaboration allows us to focus on the development of the detectors, and we were able to reduce the development time of the satellite. The satellite has a total mass of about 8 kilograms, and the power consumption is about 16 watts. So NinjaSat has two types of payload, which were developed by NinjaSat team in Riken. In the top and bottom part of the satellite, you can see the two non-imaging gas multiply counter, or GMCs. And in addition, radiation belt monitor are also installed next to the star trackers. So left picture shows the flight model GMC. GMC is a 1U size non-imaging gas X-ray detector, and it is a primary science payload of NinjaSat. GMC mainly consists of three components: gas cell, which serves as the X-ray sensor, front-end card for high voltage supply and signal processing, and data acquisition boards. So all of these components are housed within a very compact 10 centimeter cubic. So lower left figure shows the cross-sectional view of the detector. Incoming X-ray pass through a collimator above the gas cell, and then absorbed in the gas mixture via photoelectric effect. The generated electrons are then amplified by a gas electron multiplier, or GEM. This is used for the electron amplification and has been developed over many years in our laboratories. So as shown in the photograph, it is a thin seed-like structure with numerous tiny holes. By applying a high voltage of about 600 volts, the number of electrons can be multiplied by roughly a factor of 500, significantly improving the signal-to-noise ratio. The detector energy bandpass is 2 to 50 keV, To achieve this wide energy range, we used xenon-based gas mixture. An X-ray collimator defines the detector's field of view to be 2.1 degrees. By combining this detector field of view with the satellite attitude control, we can observe point X-ray sources. The most significant feature of the GMC is its large effective area, about 32 square centimeters at 6 keV, which is the largest among previous detectors on board CubeSat missions. So here is why we choose a gas detector for NinjaSat. There are three main reasons. So first, a gas detector provides a large effective area at a low cost. Compared to other type detectors, such as semiconductor detectors, it is cheaper, and using a larger gas cell allows us to easily achieve a large detection area. So second, it can operate without temperature control. In CubeSat mission, space and powers are strictly constrained. So, and many other detectors, such as semiconductor detectors, require temperature control system. But that is currently not easy to implement in CubeSat missions. So finally, we have extensive development experience with GEM detectors. So for example, Riken Tamagawa Laboratory provides a GEM for IXP satellite. So by using the space-proven GEM, we were able to reduce development time for NinjaSat. So here is a project timeline. We started the NinjaSat project in 2020s and took about 2 years to develop the payload and ground calibrations and space environment testing. So here's a picture of the main component of the GMC. We fabricated the first GMC flight model in 2021. For picture on the left side shows the component of the gas cell, which is the X-ray sensor part. And the right figure shows the electrical board, FECs, and the DAQ board. So after the components were fabricated, we assemble them in a clean room. So this picture shows the step-by-step assembly of the GMC. We have assembled one engineering model and 4 flight model GMCs, and then we selected 2 of them for onboard satellite. So, and we conducted vibration test and thermal vacuum test as a space environment testing. But we will skip. I will skip the detail here. But to perform astronomical observation in space, the instrument first needed to survive the launch environment. So it must withstand strong vibration during the rocket launch. And we also needed to make sure it can operate properly in a vacuum condition. So we conducted these qualification tests, and the GMC successfully passed all of them. It was then integrated into the satellite and prepared for launch. So finally, the satellite was launched on November 11th, 2023 by SpaceX Transporter-9 missions. So we conducted astronomical observation for about 2 years. And just 2 months ago, the satellite, as shown in this figure, the satellite has re-entered as the atmosphere as expected. So from here, I'd like to show some results obtained in in-orbit operations. So after satellite commissioning, we started payload verification in orbit. The left figure shows the result of X-ray acquisition test of GMC using iron 55 calibration source. The calibration source is mounted on the collimator as shown in this picture. This source emits mainly 5.9 kb X-rays, and its count rate was adjusted about 1 count per second after the collimator. So we can use this emission line to calibrate the detector energy scale. The energy resolution was about 20% in full width at half maximum, which is consistent with pre-launch measurement. In addition, we also conducted timing verification using Crab Nebula. Crab Nebula is a standard candle in X-ray astronomy because of its well-known X-ray pulse period of about 34 milliseconds and its energy spectrum. So as shown in this figure, we clearly detected the pulsation as expected. And from this observation, we confirmed that GMC operates as expected in orbit and proceed to the astronomical observation of X-ray sources. So here is a summary of NinjaSat observation. During its 2-year operation, NinjaSat observed 32 X-ray sources. Right figure shows the source distribution in the galactic coordinate, mainly neutron star and black hole X-ray binaries. We confirmed that NinjaSat has a high X-ray sensitivity among CubeSat utilizing the gas X-ray detector for science payload. Thanks to this sensitivity, we successfully demonstrated that even a small CubeSat can observe more than 90 X-ray sources. And so far, 3 papers have been published, and another one was just accepted recently. In addition, data analysis for other sources is ongoing. So, and finally, I'll talk about the observational results obtained with NinjaSat, especially X-ray busters. So in this part, I'll introduce 2 types of observation that take advantage of NinjaSat unique capability, long-term monitoring and prompt follow-up observation of X-ray transient event. So first, let me start with the long-term observations. So I show the result for our first science target, the clocked X-ray buster SRGA J1444. This source is an accreting neutron star, as I already mentioned. So gas from the companion star accrete onto the neutron star surface and X-ray bursts occurs. So this figure shows the average burst light curve observed with NinjaSat. You can see the rapid increase in X-ray intensities, and the burst duration is about 20 seconds. This is the first detection of X-ray burst with CubeSat missions. And so X-ray bursts are very bright phenomena, so they can be detected relatively easily, even with small detectors on board a CubeSat. However, NinjaSat enable us to detect not only X-ray burst, but also the percent X-ray flux, which is much fainter than bright X-ray burst. So here is a result of long-term monitoring of percent X-ray flux observed with NinjaSat, along with the data points from All Sky Monitor Maxi. So horizontal bars indicate observational interval by other satellites such as NICER, IXP, NewStar, and IXP. So as you can see, the 25 days observation by NinjaSat covered almost the entire decay phase of this outburst, which is the longest continuous coverage, except for the All Sky Monitor Maxi. And NinjaSat, the flux history observed with NinjaSat is constant with that of Maxi, but NinjaSat achieve better, higher sensitivities. So this is because NinjaSat has a comparable effective area and a much longer exposure time compared to Maxi. So therefore, NinjaSat enable us to detect not only X-ray burst, but also finer variation in percent X-ray fluxes. So here's a comparison between the burst profile of SRGA J4044 and the prototypical clocked X-ray burster GS1826. So burst from SRGA J4044 has a duration of about 20 seconds, much shorter than the typical value of 100 seconds of GS1826. So this indicates that the heating by the RP process, which occurs in proton-rich environment, is weaker in SRGA J4044, resulting in a shorter burst tail. So in other words, the companion star may be relatively poor in hydrogens. To check this idea more quantitatively, we work together with a theorist. So here you can see the comparison between the observed data and theoretical models. The black data point shows the observational result from NinjaSat, and the blue line represents the model with solar elemental compositions. So as you can see, the solar model cannot reproduce the burst tail part. So eventually, we found that the burst is well explained by the red model, which has about 10% less hydrogens. So this is the first example of a clocked X-ray burster with a non-solar elemental composition. And this graph shows a relation between the burst recurrence time and the burst durations. Both parameters are independent of the source distance, so useful for comparing observations and theoretical prediction across different sources. The theoretical modeling successfully reproduced the observed relation with the Helm-enhanced accretive funnel, making this source the first clocked burster with non-solar compositions. So furthermore, we investigate whether we could constrain the neutron star mass from the relation between the burst recurrence time and the percent flux. As I mentioned earlier, for clocked bursters, the recurrence time is known to be roughly inversely proportional to the percent flux, as shown in these equations. The right figure shows the result for SRGA J1444. The horizontal axis represents the percent flux, and the vertical axis is the burst recurrence time. From our observations, we obtained the parallel index of about 0.84. So comparing this with the previous results summarized in this table, we find that the SRGA J1444 shows the smallest eta value, parallel index value ever measured, and it is our first source with eta significantly smaller than 1. So theoretically, this parallel index eta is suggested to depend on the neutron star mass and the equation of state. So red figure shows the theoretical calculation of eta as a function of the neutron star mass. So as you can see, eta decreases as the neutron star mass increases. So this trend provides a link between the observed eta value and the neutron star masses. So here we overplot the previous observation result together with our result on the theoretical curves. So as you can see, the previous 5 clocked burster all have eta value constant with or larger than 1. So in contrast, our result for SRGA shown by red line is significantly smaller than 1. So this indicates the observed eta value cannot be explained by a model with neutron star mass below about 2 solar masses. So in other words, our result suggests that the neutron star in this system may be relatively massive. So, but to make a more detailed comparison between the observation and theory, we need to additional calculation that extend beyond 2 solar masses. And this work is currently in progress in collaboration, and we plan to refine our study in the near future. So next, I'll show the result that take advantage of the flexibility of a CubeSat. The target is prototypical clocked X-ray buster, GS8026. It is the best studied clocked X-ray busters, and as I mentioned earlier, its recurrence time gradually decreases from about 6 to 3 hours with increasing accretion rate, as shown in this figure. So, however, the clocked bursting behavior has been observed only in the hard spectral state. But the source has remained in the soft state since 2015. So the right figure shows the long-term X-ray light curve of this source in the 2 to 20 kb range observed with the all-sky monitor MACSI. So the bright phase corresponds to the soft state, where the burst recurrence time becomes irregular. So making that makes it difficult to compare the observation with theoretical models. Therefore, many researchers of X-ray busters has been hoping for this source to return to the hard state. So fortunately, in May this year, the source transitioned to the hard state for the first time in 10 years. There are no alerts from any all-sky monitors, but NinjaSat began observation shortly afterwards, taking advantage of the operational flexibility of the small satellite, and successfully captured this transient hard spectral episode, lasting about only 10 days. So here's the observational result from NinjaSat. So NinjaSat started monitoring of the source when it enters a hard state and continue until the source returns to the steady soft state. So during this period, we detected total of 19 X-ray bursts, 14 in the hard state, 4 in the transitional state, and 1 in the soft state. So in the hard state, we identified a new clock bursting epoch, where the burst recurrence time was remarkably stable, about 1.6 hours. So this confirms the return of periodic bursting behavior in the hard state for the first time in 10 years. So here we show the persistent and burst emission in the hard state. The left figure shows each energy spectrum. The persistent emission can be well described by a single computation model. On the other hand, burst emission is can be reproduced with computation model plus blackbody model. In the right panel, we present the result of the time-resolved burst analysis, showing from top to bottom the flux, blackbody temperature, and blackbody normalizations. So the magenta data point represents our observational result, and the other 3 data correspond to previous epochs. So as you can see, the peak flux of this burst is about 20% lower than in previous epochs, which can be attributed to the smaller blackbody normalization. So interestingly, the recurrence time we observed this time does not follow the previous established power law relations between recurrence time and the persistent flux. The top panel shows these relations. A black circle represents previous observations, and the dashed line indicates the theoretical curve with a power index of about 1. So our new data point shown as a red circle, red square, is about 40% shorter than the expected recurrence time based on the observed percent flux marked by the green stars. So this result suggests that there might be anomalous ignition conditions for the burst. So we looked at other observable shown below. Interestingly, as shown in the middle and bottom panel, both the burst fluence and the black body normalization during the burst tail are also smaller than expected from the previous linear trend. So notably, the reduction rate of the black body normalization closely match that of the recurrence time. So in our paper, we propose that these observational results reflect funnel accumulation over a smaller fraction of the neutron star surface, as illustrated in the schematic view on the right. So burst ignition is a local phenomena. So once ignition occurs in certain region, it quickly spreads across the entire surface. Therefore, it is necessary to consider the global accretion rate and the local accretion rates separately. So the local accretion rate is inversely proportional to the accretion area. So from this, we can easily derive that the total accumulated mass between bursts is proportional to the accretion area. So if the funnel accumulation over a smaller fraction of a neutron star surface, the local accretion rate becomes higher than in previous epochs, leading to a shorter burst recurrence time. So as shown in the figure on the right, this simple localized accretion model can naturally explain the observed short recurrence time together with the smaller black body normalizations. So, so as illustrated on the left, the accretion region may shrink with increasing global accretion rate. So this scenario needs to be verified through multi-dimensional simulations. So this result is important because our result highlights that even for the best studies clock text reverser GS8026, more realistic modeling, including multi-dimensional effect, could be important. So finally, I'll show another result from NinjaSat prompt follow-up observations. So in November last year, a new X-ray transient, MAXI J7052, has discovered. As shown in the figure, the all-sky monitor MAXI detected an X-ray brightening from a position where no point source had previously confirmed, and confirm it as a new X-ray transient source. So half a day after the discovery, MAXI reports the result to the astronomers telegram, and only 2.5 hours later, NinjaSat began follow-up observations. So as I mentioned earlier, NinjaSat has a higher sensitivity than MAXI, which allows us to monitor the source more accurately, especially during its faint phase. So to investigate the nature of this transient X-ray source, we divided the observational period into several intervals and performed spectral analysis for each interval. So here's the result of the spectral analysis. So the left panel shows the time evolution of the spectra in the 2 to 20 kb range. So each spectrum was fitted with the black body model, and the lower panel displays ratio between the data and model. So as you can see, all spectra are well described by the black body models. And the right panel shows the time evolution of the flux, black body temperature, and the black body radius obtained from the fitting. The black body radius remained nearly constant around 10 kilometers, which is comparable to the neutron stars, neutron star radius. On the other hand, the black body temperature decreases from about 1.8 keV to 0.6 keV. So these results indicates that the observed X-ray brightening shows a similar property to an X-ray burst, but with a much longer duration than a normal X-ray burst. So in addition to normal X-ray burst, there are longer duration event known as intermediate burst and super burst. So this table summarizes their characteristic properties. The duration, as we move downwards, the duration becomes longer and the total energy increased. So as illustrated in the figure on the right, longer bursts are thought to ignite deeper funnel layer, and in the case of super burst, carbon burning is believed to play a key role. So our observation shows a burst duration of about 3 days with a total energy release of about 10 to 42 ergs. So which that is consistent with super burst properties. So to test this idea more quantitatively, we compare the observed light curve with the theoretical cooling model of the neutron star surface proposed by Cumming et al. So as shown in this equation, the model describes the flux evolution as a broken power law functions. The red line shows the best fit model, which can reproduce the observed light curve very well. So our results suggest that the emission originating from the carbon ignited superburst. So thanks to the prompt follow-up observation by NinjaSat, we were able to reveal the nature of Mach CJ1752. So here is a summary. NinjaSat is a CubeSat X-ray observatory designed for bright X-ray sources. So during its 2-year operation, NinjaSat observed 32 X-ray sources using 2 gas multiplier counter, which has the world's largest effective area among CubeSat missions. So I showed the pointing observation with CubeSat can provide variable astronomical X-ray data, especially for the studies of X-ray bursts. And in addition, as a member of our team, currently analyzing data from additional sources, other sources, and we hope to show some result in the near future. So furthermore, based on the success of the NinjaSat project, we have started the development of NinjaSat 2. So that's all from me. So thank you for your attention.
Takeda-san, thank you for your nice talk.